Hello and welcome. I am Dad, and today I will be talking to you about the multi-cycle data path. So first off, what does multi-cycle mean? Multi-cycle means that the instructions are computed in multiple clock cycles, whereas for the single cycle data path, all of the instructions are computed in one single cycle. Each of the steps of the instructions takes one clock cycle, and each of the unit in the system can be used more than once in an instruction, as long as it is in a different cycle. It must be noted that the data will only be available in a register for one single cycle after it is set in the register. So, if you don't use the data immediately, in the next cycle, the data will be lost and must be computed again. Multi-cycle data path has something called external registers to store data between cycles. And as said before, the data is only stored for one cycle. Single cycle does not have any external registers. For multi-cycle data path, instead of generating all the control signals at the beginning of the instructions, new control signals are generated in each cycle. So, why do we use multi-cycle instead of single cycle? Well, multi-cycle data path reduces the number of hardware needed for any given instructions. Because hardware can be reused, there is no need for separate hardware for each of the minute tasks. Multi-cycle data path also reduces the average instruction time. Because modern CPUs are so fast, they can ram through the multiple cycles extremely quickly. Also, in single cycle data path, the clock cycle duration is the time of the longest instruction. The clock cycle duration is dynamic for multi-cycle data path. Now let's talk about the external registers. There are the IR, which is the instruction register, A, which is the ALU register, so is B, and the ALU out is the ALU register that stored the ALU computation results, and the MDR, or the memory to data register. There are 32 of the instruction registers, and the A or B are used to compute the ALU computations. ALU out is used to store the ALU results, and the MDR is used to write memory data into the register. Now, almost all of these control signals can be used together depending on the instruction type, except for memread and memwrite. These are mutually exclusive. Let's start looking into the number of cycles needed for each of the instructions. As you can see from the table, the first two cycles are the same for all instructions. This is because the system does not know what opcode was given until the very end of the second cycle. So to not waste time, the branch address is computed beforehand. In the first cycle, the instruction is fetched, so the data goes from the memory of the PC address to the instruction register, and the PC is updated to PC+4. In the second cycle, RS and RT register is stored at register A and B respectively, and the branch address is computed, and the opcode is decoded. Branch and jump are the shortest instructions. This is because after knowing the branch address and the opcode, in the third cycle, they can just match the opcode. So if the opcode is branch or jump, they can just jump straight to the address computed in the second cycle. For R-type and store, it takes 4 cycles to complete. This is because in the third cycle, for R-type, there is the ALU operations where A is added, subtracted, or divided by B, and the result is stored at ALU out. And in the fourth cycle, the result is then written into the destination register RD. As for store, in the third cycle, the memory address is computed, and then in the fourth cycle, the data in register B is written into the address of the ALU out, so the address that was computed in the previous step. Load instruction is the longest, as it takes up to 5 cycles to complete. In the third cycle, it computes the memory address just like store. In the fourth cycle, it pulls the data from the memory and store it into the memory data register. And then in the fifth cycle, it uses the data from the MDR and write it onto the register RT. Now, let's trace through the R-type instructions. In the first cycle of the R-type instruction, the instruction is fetched from PC. It goes from PC through the MUX to the memory and then to the instruction register. Then, the PC is updated. It is done so by sending its signal to the ALU so that it can be incremented by 4. Then the resulting address is then sent back to the PC via this route. Then the PC is updated. In the second cycle, the data from register RS and RT is sent to register A and B respectively. Then, regardless of the opcode, the branch address is calculated. This is so that the CPU does not have too much of an idle time. The branch address is calculated by sending the PC back to the ALU and also send to the ALU the immediate value, sign extended and shifted left by 2. Then the resulting branch address will be stored in the ALU out register. It is also in this cycle that the opcode is calculated. The opcode is decoded within the instruction register. Now, in the third cycle, for the R-type, the calculation is done. So the data from A is sent to the ALU as well as the data from B. Then the control will send the opcode to the ALU so that it knows what operation it should be doing, be it plus, minus, divide, or multiply. Then the result will be sent to the ALU out. And finally, in the fourth cycle, the result in the ALU out will be sent all the way back to the MUX through the memory and then into the instruction register, and it is stored at register RD, the destination register, this one. And that's it for the R-type instructions. Next up, let's trace the load instruction. The first cycle for the load instruction is the same as the one for the R-type instruction. The instruction is fetched from the PC and is sent to the instruction register. Then the PC is updated to PC+4, and the new address is sent back to the PC. Then it's the same for the second cycle. Register RS and RT's value is sent to register A and B respectively. Then the branch address is calculated by sending the already incremented PC back to the ALU, as well as the offset, the immediate value with the sign extend and shift left by 2. Also in this step, the opcode is decoded. Next, in the third cycle, this is where it will be different from the R-type. Instead of doing normal calculation, the memory address is computed by sending the address from register A to the ALU and the immediate offset sign extended, but this time not shifted by 2, to the ALU, and the resulting address will be stored in the ALU out register like usual. Then for the fourth cycle, fetching the data from the memory address calculated in the previous step and store it into the register MDR so that it can be ready to be written into the register in the next cycle. And finally, in the fifth cycle, the data is moved from the MDR back into register RT, so that RT can be updated. And that's it for the load instruction. Now let's do the store instruction. Since the first and the second cycles are the same for all of the instruction types, let's just skip over those and go straight to the third cycle. In the third cycle of the store instruction, the same procedure happens as with the load instruction. The data from the register A is sent to the ALU, as well as the non-shifted sign extended immediate offset, so that the ALU can calculate the address of the data, and the address will be stored at the ALU out register. Then, in the fourth cycle, instead of reading the data from the ALU like with the load instruction, in the store instruction, the data from the register B is written into the address that was calculated in step number 3. Like so. And that's it for the store instruction. And then let's do the branch next. The branch instruction is pretty simple. In the third cycle, the control will check to see if the opcode is the same one used for the branch. Then it will check the instruction A minus B to see whether the result is true. If it is true and the opcode is branch, the branch address from the ALU out calculated in the second cycle is sent back to the PC so that the PC can branch to the calculated address. And if the calculation results in the true, the ALU will send a true signal to the PC write conditional so that it can tell the PC to branch to the calculated address. And that's it for the branch instruction. And finally, let's do the jump instruction. Jump instruction is the shortest instruction of all. In the third cycle of the jump instruction, when the control confirms that the opcode is the one for jump, it will just send the jump address to the PC so that the PC can jump to the new address. And that's it. No calculation whatsoever. It's just that fast. Here are the control signals for each of the cycles of the instructions. You can look at it in your free time. Alright, let's do some exercise. First off, modeling the path of the store instruction, come up with the instruction sets and the control signals for the store word increment. Its functional form is given as the data of the register RT is stored at the memory address of register RS with an immediate offset. Then the RS address is incremented at the end. The instruction set for the store word increment follow almost the exact same procedure as with the regular store word instruction. The procedures are the same all the way from the very first instruction to the end of the third instruction. In the fourth instruction is where the difference start to appear. So in the fourth instruction, like usual, the data from register B is written into the memory address calculated in the previous part, calculated in cycle 3. Like that. Then the address of the register RS that is stored in A will be incremented by 4, and then that is the result is stored in the ALU out register. Then in the fifth cycle, the newly incremented RS address will be sent back to register RS so that it can be updated. And that's it for the store word increment. It's very similar to the regular store word. So here are the control signal for store word increment. As said before, the first 3 cycles are the same as the store word. And in the fourth cycle, IORD is set to 1, memwrite is set to 1, ALU source A and B are both set to 1, and then ALU op is set to 0, 0. Then in the 5th cycle, rec-write is set to 1, mem-to-rec is set to 0, and rec-des is set to 2. For our second exercise, let's come up with the instructions as well as the control signal for the load word increment based on the load instruction. Its functional form is given as the data from the memory address of register RS with an immediate offset is sent to the register RT. Then, at the end, the address of RS is incremented, just like with store word increment. Just like with the store word increment, the load word increment has very similar add-ons. The only difference is that instead of the add-on appear in the 4th cycle, the load word increment add-ons will appear in the 5th cycle. So in the 5th cycle of the load word increment, like with the load word, the data from the memory data register is written into the RT register. Then the RS address in A is then incremented by 4, and the result is stored in the ALU out register. Next, in the 6th cycle, the newly incremented RS register will then make its way back to the RS register so that the register itself can be updated. And write register. And that's it for the load word increment. And similarly, in the 5th cycle of the load word increment, ALU source A and B are both set to 1. The opcode is set to 0, 0 for add. Rec-write is set to 1. Mem-to-rec is set to 1. And rec-des is set to 0. Then, in the 6th cycle, rec-write is set to 0. Mem-to-rec is set to 1. And then rec-des is set to 2 to update the RS register. And that will be it for the lecture today. Thank you for listening.